Hello, and welcome to Our Future in Space. I'm your host, Dr. Jeff Greenblatt, the Vice President for Science and Research at Orbital Assembly Corporation. In this podcast, we will explore the technical, economic, social, political, and ethical considerations of moving humanity into the solar system to work, play, and ultimately to live. Our species is at an inflection point in its evolution, where we now have the ability to sustain life off-planet in Earth orbit and soon throughout the solar system. And this is happening for several reasons: the dramatically falling cost of launch, the exponential growth of computation, the rapid commercialization of low Earth orbit, and a growing concern that humans are outstripping our planet's resources. Do we merely survive on this planet or expand outward into the solar system and thrive? And I am here today with my co-host, Eric Ward, who is the Vice President of Engineering Design at Orbital Assembly. How are you doing today, Eric?
Oh, I'm doing just great. I'm excited for this interview. We've got our very own Tim and Tom. Let me give you guys a little introduction. Dr. Tom Spilker is OAC's Chief Technical Officer. He's one of the co-founders, and he leads OAC's space system development. Before OAC, Tom was a consultant on spaceflight mission architecture for planetary and solar system science space missions, and he has served as both a scientist and an engineer at NASA's Jet Propulsion Laboratory for over 20 years. Tim Alatorre, NCARB, is also co-founder at OAC, and he's the Chief Operating Officer, where he leads the habitat design. Before OAC, Tim was the CEO of Domum, an internationally recognized architecture firm based in California. He also served as a planning commissioner and member of a municipal architectural review committee for the city of Rockland, California, and worked as a consulting subject matter expert for the state. Welcome, both of you guys.
Thank you. It's great to be here.
Yep, very, very excited to be here. I've heard lots of good things about this show, so glad to be a part of it.
Yeah, we thought we'd have you both on to contribute. You're definitely both leaders in the space industry in your own right. So,
well, you've had a number of really exciting guests, and I've enjoyed listening to the varied topics and going in depth in areas where typically we don't have a chance to talk with experts about those things. So, Tom and I have a high bar to live up to today.
Well, and it's great to have us both on at the same time, being architects of different aspects of the space systems, the actual space systems that make the thing fly in space, and the thing that makes it possible for humans to be there, the habitats that Tim is covering. As I've said before, I design things so that people don't blow up, and Tim designs them so that people don't throw up.
Keeping machines intact is actually quite a bit easier than keeping people intact.
Yes.
There's so many variables. People are
you both have your work cut out for you, though, for that. Yes. For sure. Well, maybe we can start, Tim, with explaining just both what you do at Orbital Assembly Corporation, but also the path leading up to that, because you haven't always been in the space field, and I think you've been interested in a long time. But yeah, maybe you can tell us about your path to this point.
Yeah, Tom and I, I think we both kind of started our careers in the same way, which was a passion about space and wanting to do something with space. I never really saw it as a possibility. Where Tom, he was just dead set on it and has dedicated his career to it. But I took a different path. When I was in really my formative years, elementary school, middle school, high school, I was really excited about flight and space. I grew up in Southern California, not too far from Edwards Air Force Base, and was able to go out to the base there and see the orbital, for the space shuttle, that hardware there, and SR-71, air shows, so many things. I took a number of courses in high school in our local area about flight and started kind of going on the path of being a pilot. And I got distracted with architecture. And I wouldn't say really distracted. It kind of called to me, right? I love the whole process of designing and building things that people then get to interact with. And I think some of my most rewarding experiences I've had have been where I have a concept or an idea in my head, and then many months or years later, being able to see people interact with that space. One jumps out of my mind. We were working a number of years ago, worked with the San Francisco Giants in San Francisco. And if you've ever been at the stadium there, the stadium's right on McCovey Cove, and right across from the waterfront, there's this big parking lot area. And we had the opportunity, my firm and I, to design, and well, we were, it was a big team of people, but we got to help with the implementation of this outdoor pop-up kind of retail space where people could come as a beer garden. There was food trucks and seating and merchandise sales. And during game day, they would roll out all this furniture onto the street there. And it was so rewarding to go out there one day when the project was completed and just see thousands of people enjoying something that I had a hand in creating, right? And so that becomes really addictive. And I've built tens of thousands of structures all over the world and billions of dollars of construction. And now taking those ideas of development and creating spaces that people enjoy to spend time in to space, and this really a new frontier. Yes, we've been having astronauts in space for a long period of time, but now making the effort to get people in space, like the everyday person, for long periods of time. It's just really an extension of everything I have done. It's not, especially with Tom Spilker, working on this with us. It's not. He worries about the really hard space stuff, and I can focus on the people stuff, right? And what I do with Orbital Assembly Corporation, you asked me to tell you that. So I wear a number of different hats. We're still in a startup phase, so we're all doing a whole lot of different things. And most of my day, unfortunately, really is spent doing a lot of the administrative and executive tasks. And then I get to squeeze in design work here and there. I look forward to, here's for those listening or not able to see the screen, here is one of the early renderings of our bar area in the Voyager station. But I really enjoy and get a lot of satisfaction out of doing design work. And I design to relax. It's not really my work, right?
Yeah. Although has and will continue to play a pivotal role, once we're actually in the building phase. Well, maybe let's turn to you, Tom. And so you described sort of in a nutshell, you design stations so people don't blow up. But like, what are you mainly focused on these days, or what are you most passionate about in your work with Orbital Assembly Corporation? Wherever you'd like to take that.
Oh, well, like Tim was saying, it's really good. It's fulfilling to see an idea that you've had become a reality, and something that you thought, oh, well, it should be this way, and here's what the design should look like, that 3 or 4 years later, it's headed out of the solar system at 30,000 miles an hour or something like that. I worked on Voyager and worked on Cassini and worked on Genesis. And unlike Tim, most of the stuff that I've worked on, you can't show to anybody because it's either headed out of the solar system or is already out of the solar system, or it burned up in Saturn's atmosphere or something like that. But the return from those things, seeing that the ideas that I and a whole team of people had early on came back as, well, now we know something about the universe that we didn't know before, and it's something very important. And this is what I'm seeing with Orbital Assembly, being able to think about what is it we're trying to do, what exactly are we trying to do, and figure out in very uncertain terms, what do we want our system to do, and translate that into something that actually accomplishes that. And does it in a way that doesn't come apart, doesn't explode, doesn't make people suddenly lose their oxygen because a bulkhead broke or something like that. And it goes the whole gamut from thinking of very general things, the general requirements that we want to do, down to very specific things. okay, if we want to have a module of this size, that means we're going to need to support this much weight when it's in rotation, and that means we need to have these kind of connectors, and that means we're going to need these kind of bolts to hold those connectors together. And you transition all the way from the very big picture to the very detailed, the thread pitches on bolts and so on.
Mm-hmm.
And
yeah, it's
covering
amazing that you
entire
can
range is very rewarding. Being able to go from the general picture down to the bolt pitches.
Yeah, if I could
Yeah,
just add one thing to
please.
too, like we've kind of made this division of roles between Tom and myself, and in a high level, definitely there is. But you know, one of the things about being a designer or an engineer, which I think both Tom and I are engineers at different skill levels and designers. Definitely on the architecture side, there's a lot of terrestrial architecture, right? There's a lot of design and system integration, and I'm a licensed practicing architect. I have licenses in a number of states. And so part of that is having a breadth of knowledge in a lot of different areas. And Tom as well, yes, his craft have been sent out into space, but he's got years and decades of experience in a number of different fields. And I think that's one of the real strengths of our team is we're multidisciplinary. No one is really like ignorant in a broad spectrum of things. We all have a certain amount of ability and skill level across a wide range of topics. And so I understand thread pitch. I don't want to do the math to calculate how strong the bolt is. I'll let Tom or Eric, you do that, right?
Yeah.
And I think that's important. Everyone needs to understand, at least at a high level, what's going on. And our team is really good at that.
Mm-hmm.
Which I enjoy.
And there's a second really good benefit from having these overlapping roles, and that is if somebody does a calculation and they slip, and somebody else sees it and says, well, do you think that's 10 or is it actually 100? Everybody has the capability to go in and check what somebody else has done and make sure it's right.
Yeah. And sometimes it's just the high level question where we may actually be ignorant of the math or physics behind it, but we can still say, does that really work? Can we do that?
Does it make sense?
Right.
Yeah, that common sense check is something that Tom, you worked with a lot of engineers through your career, as have I, and there's people who are really good at crunching numbers that aren't really good at those common sense questions, and so that's that gut check and just understanding that something really is possible, that the numbers make sense with reality. You know, those are questions that I think our team is good at bringing up and identifying.
I saw an example of that at Caltech once, where in a class where you're supposed to figure out how to do back of the envelope calculations, somebody messed up a calculation and was in error by 10 to the 50th power.
Oh my goodness.
Oh. Wow. Okay. Well, yeah. Hopefully it doesn't take a special person to notice that big of a discrepancy. Sometimes we can get buried in the noise.
In this case, the answer was 10 to the 130th, and the answer they came up with was 10 to the 80th.
Yeah.
Mm-hmm.
And you know, that's hardly intuitive.
Yeah.
Yes, indeed. Well, maybe we can talk a little bit about, since you said the word, I think a minute ago, reality, maybe we can talk about what we are trying to build into reality, and talk a little bit about the project that Orbital Assembly is working on right now as a stepping stone to bigger and larger things, hopefully one day. Either of you want to introduce that?
Well, maybe if I could just take a step back.
Sure.
You know, why are we building space stations? And that's that whole concept is what really brought the four of us together to begin with the idea of getting large numbers of people on orbit to live in a healthy way, right? And microgravity, we know, is really bad on the human physiology, and so that led us on the path of artificial gravity stations and rotation. And images have been out here for since that was a rendering and the design of Voyager that we did back in I guess that image actually was from like 2021, just last year. But the design of Voyager, well, that started in what, 2018, somewhere on there,
well,
Tom?
My first drawing of this kind of geometry was May 2nd, 2019.
Yeah. And then, And then orbital assembly, we incorporated towards the end of 2019 with the goal of making large stations like this possible, right? And something that we've done over the last couple of years is really started to get into the market studies and understand where the demand is and how we can, frankly, finance, right, stations of this size. And so a stepping stone to that, which allows us to validate the technology and feed forward everything into the Voyager class station, is our Pioneer class station. And we actually just made a formal announcement about that in a press release, I guess it was last month. But we had leaked some information about this with the NASA CLD proposal last year. And what's really exciting about this is this isn't like a departure from Voyager. It's a stepping stone to Voyager, and it's going to allow us to get to Voyager faster, which I'm excited for.
Yeah. So can you speak a little bit to that stepping stone? How do you architect a space station, that's small, but is a stepping stone to something that, is much, much bigger in this case?
Well, modularity is a key there. If you build pieces that can be used in multiple ways, like a habitable module that can be configured in different ways in the interior, but has standard connections to the exterior, so you can connect it to other modules or access tubes, tunnels, things like that. There are a lot of different configurations that you can put together with those pieces. And this allows you to test different configurations to put small things in orbit that will test the pieces that you use for much larger things later on. It also allows you to test such things as the dynamics of rotation. How do you control a rotating space station and make sure that it keeps its solar rays pointed where they should be, keeps its communication antennas pointed where they should be, and in the parts of the station where you've got microgravity, that rotation isn't bothering the microgravity.
Yeah, and on the screen here right now, you're showing a section cutaway of a microgravity module. And these aren't trivial in size. These are roughly 400 cubic meters. And these modules, the current Pioneer class station that we're getting ready to launch and build here, it's going to be larger than International Space Station in volume and definitely in capacity, right? We're going to be able to have, in fact, I was just talking, sorry, tangent. I was just talking,
sorry.
I guess it was towards the end of last week with a potential customer who's a well-known brand. I can't really talk about them yet, hopefully soon. They've been running experiments on International Space Station for a number of years, 3D printing organs, building fiber optics, doing experiments with thin films. And the customer base for these types of applications just can't operate a business on International Space Station, right? Just getting things on station and the requirements that are needed to operate on station are really opposite of a business case. And then I don't know how many people know this, but if you want to hire a NASA astronaut on the International Space Station to do something, you have to pay them $180,000 an hour. That's the current going rate for a NASA astronaut. And companies are limited to only 25 hours of crew time per year. So if you think about any kind of factory that's building something of any kind of usable scale, you're not going to do it paying your staff $180,000 an hour and less than 25 hours a year. So what this company has done is they've relied heavily on automation to where they only have maybe an hour of crew time for any given run of any experiment, 30 minutes or so getting it installed and 30 minutes getting it back off. And then the downside of that is the automation, you end up paying for a lot of NRE, non-recurring engineering, to develop a process that might not go anywhere, right? It's an experiment, it's a research project. And so what we're offering with Pioneer Station is crew time at a much lower rate than $180,000 an hour and really unlimited crew time. You could have somebody working 40 hours a week, for 50 weeks out of the year, and you can actually run a business. And with the volume that we have on our stations, now companies can actually make fiber optics at scale. They can actually make 3D printed organs and do stem cell at scale. Doing experiments right now on ISS, you're limited to basically, a locker, which is like the size of a microwave,
Mhm.
You really can't swap out express racks, so you're locked into the architecture on ISS. And we're designing a station for business, right? It's
I mean,
it's a different paradigm.
And excuse
yeah,
me,
it
I
was
might,
never designed. Yeah,
while
go
you've
ahead.
got the image up there, for those of you that are not accustomed to translating metric unit volumes to linear dimensions, the thing that you're seeing there is about 35 feet from side to side and about 21 feet top to bottom.
Yeah.
Yeah, quite a lot of space. So multiple cabins that can be rented, leased, by the day, week, or month, and reconfigurable, so you can have different kinds of operations going on there over time.
Yeah, that's one of the key
really
things
exciting.
is not being locked into one particular layout. So this interior design here, which is preliminary, we'll see exactly how it gets fleshed out when it comes time to launch. But my idea behind this was everything is modular and can be broken down into very small components. So you can launch everything disassembled in even like a Dragon capsule and take it up there and build out the structure with a little bit of crew time. It's basically an IKEA for a space station, right? We'll give some nice instructions with Swedish translations.
That's right, but kind of leave people to their own devices. So we were kind of establishing, ISS. Obviously, it was the first truly, long-term space station that was designed to do a lot of science, but it was never really intended to be a commercial operating station, and that's where we're seeing the limits of this now. And as the industry has been moving more toward commercial operations, I think the approach, the paradigm is quite different, right? Really make it customer focused instead
Right.
of
for the first time, it's actually affordable to get things to and from orbit to where businesses are interested, right? And Tom, you've got all these numbers off the top of your head. Maybe you can just talk a little bit about the shift in launch prices, because I know you've talked about it a little bit on your show previously, Jeff, but that's really changing everything.
Yeah. For about 50 years at the beginning of the space age up until about 2015, if you corrected for inflation, the price of sending a kilogram to space was rarely less than $8,000. It was generally between $8,000 and $9,000 per kilogram to send anything into space, any mass. Humans got more expensive because you have to send a lot of support equipment along with them. But it was between $8,000 and $9,000 to send up a kilogram. Now, some launch vehicles trying really hard were able to get that up to over $20,000 a kilogram, and in one measure up to $64,000 a kilogram. But you had to try really hard to do that.
Was that the space shuttle, for
Yes.
instance?
We weren't going to mention names there, Jeff. Yeah, I mean, if you imagine you're trying to, let's say, open an Amazon.com, and your shipping costs are $8,000 or $60,000 a kilogram, you just can't run a business that way, right?
Yeah.
And so what has happened is that the prevailing thought before about 2015 was that a launch vehicle is something that you use once and throw away. Well, Elon Musk had another idea, and other people had other ideas, but when he started hatching his idea, computer technology had gotten to the point that it could handle, in a reasonable amount of mass and a reasonable amount of power consumed and so on, the compute necessary to be able to do a return and landing, or a landing on a ship in a downrange position. And people were still very skeptical about it, and were laughing, not behind his back, but in front of him, laughing at him for trying to do this. And then in late 2014, he actually landed one, and the laughter subsided a little. And then in 2015, he landed some more, and the laughter completely subsided. And people who had bet with their pocketbooks against this happening were suddenly hemorrhaging money out of their own pocketbooks. This landing of the first stage has brought, in the case of the Falcon Heavy, if you're launching a maximum payload to a low inclination orbit, it's somewhere around $1,500 a kilogram. So it's less than a third, less than a quarter of what the original price was. This is a huge change. And with further advances, notably the Starship, and there will be others to follow on Starship. But being able to recover both pieces of the rocket will bring prices down by 2 orders of magnitude or more. So instead of $8,000 a kilogram, you're looking at about $80 a kilogram. If that is successful, the entire landscape of what you do in space will change radically. And that's exactly what we're trying to do here. We're, before it actually happens, starting to plan on how would we use this marvelous capability to do things that were only science fiction previously.
But even right now, though, with the average of Falcon 9 and current launch platforms around $3,000 a kilogram, we're able to do things that weren't possible before. So, Pioneer is not waiting around for next gen space systems. We can operate now.
Yep, and it'll only get better because it might cost a certain amount to get the first one up, but if we can then get lower launch vehicle costs for the second, because we're not planning to build just one. I mean, this is part of a sequence.
Well, and also getting large numbers of people to orbit, right? The only spacecraft currently that we have access to take people to orbit is the Dragon capsule. And while it's a significant step forward, it's not really cost effective for the average person, right? So we need better human transport systems, and there's a lot of promise out there for bringing the cost down on that. But that's going to be the next big change.
The terrestrial analogy is if you and 399 of your friends wanted to go from Los Angeles to London, and you bought a 747, a Boeing 747, flew it to London, and then threw it in the English Channel once you landed, how much would your ticket cost? Well, it turns out that ticket cost more than $1 million. But reusing 747s, the way that we're looking at reusing rockets, those ticket prices are about $1,000. So more than 3 orders of magnitude down. And that's the same kind of benefit we'll get out of reusable rockets.
So let's assume that, the reusable rocket technology is going to happen and get down to that sub $100 a kilogram threshold that really, is a breakthrough, I think, and it will change the economics of going to space. What happens after that? What then becomes possible? And then where are we going? What maybe, what are there other breakthroughs that kind of have to happen as well before we're talking about truly having a space-based economy with, thousands or tens of thousands of people in space at any given time and manufacturing on Earth? Go ahead.
Propulsion is a big factor in that. The reusable rockets allow us to get from Earth's surface into low Earth orbit or to the moon or something like that for much less money than it would have cost before. And so there are a lot of things that we can do that we couldn't do before. But once you start thinking about going beyond the moon, and if you're talking about a space economy, it's still too expensive to bring everything you need up from Earth. Earth is at the bottom of a very deep gravity well, and fighting gravity wells takes a lot of propellant and a lot of money. So we'll be looking at extraterrestrial resources, mining the moon, mining asteroids, and so on. The moon will not be too difficult, but it's also at the bottom of a smaller, but still a gravity well. Asteroids, small asteroids, say 10 kilometers across, 1 kilometer across, it's almost no gravity well, very little there. So being able to extract materials from those asteroids will be relatively cheap once you can get to them. But getting to them is quite difficult. And using the propulsion systems, the chemical propulsion systems that we have now, it takes a long time and uses up a lot of resources like oxygen, water, hydrogen. And if you're not bringing that stuff up from Earth, that's in fairly short supply on places like the moon. So we're needing propulsion systems that go beyond the chemical propulsion systems that we have now. And ideally, we would go to propellantless propulsion systems like solar sails or some other energy rather than momentum ejection based propulsion system. I guess in Star Trek, they call them the impulse engines. Rather than going on impulse from momentum ejection, we go to something propellantless. such as reflecting photons. And that in the more distant future, tens of years down the line, that will become very important.
Yeah, and if I was to put my future, prediction hat on,
well, this is the place for that.
Yeah, definitely.
Right. I think we're going to see large numbers of people in LEO first, because that, getting the people and the need for resources in LEO then opens up these other opportunities. Getting mass from the asteroids back to their surface isn't as efficient or as useful as using those resources in place, in situ, right? So if we started to build up, and I mean, that's one of the things we're trying to do, is build up this cislunar economy, and even going out to the asteroids, by having people who have needs, who have resources that they need to consume in those places, which then spurs on that economy and eventually gets it to a point where those propulsion systems and the other space, like true spacecraft, are commonplace and in use, to where we can now start to take advantage and utilize larger areas of our near solar system.
Right. I've heard the expression a few times now on this podcast from some of our guests, that where there are people, there is an economy, because people have needs, both sort of basic human survival needs, as well as comfort needs, entertainment, the ability to do things value added. And as long as there's a reason for people to be out somewhere, then there is a whole supply chain that builds up around it. And space to space is definitely a very interesting, but I would say up till now, kind of a tenuous business case, right? I mean, it's kind of hard to get it going, because why would people want to be out there? Why, why do we need to be in space instead of doing everything on Earth?
Well, and you touch on a very important point there, Jeff. So far, space has been pretty much an expedition. You're going out camping. This is not going to bring large numbers of people to space. We don't want them just to survive like you would in an expedition. We want people to thrive. They're not just living out there, they're enjoying living out there. They're taking advantage of what space has to offer, and there are lots of good things to come from it, more than just, okay, I've got enough to eat and I've got a place to sleep attached to that wall over there.
So how do you bring those considerations in when you're designing something like the Pioneer, the Voyager Space Station, where you want people to live but also thrive, and not just camp for a long weekend?
Definitely a Tim question.
Yeah, Pioneer is a more challenging one just because of the scale, right? Voyager, we have a lot more room to play around in. With Pioneer, the gravity levels are also lower, because we have the diameter of the station, at least in its base configuration, isn't as great as Voyager. But one of the things that you get with even a small amount of gravity is you have built-in orientation of a floor and a ceiling and a walls, where in microgravity there is no clear orientation. So I don't know if you have here, Jeff, the cutaway of the one habitation quarters on on Pioneer, but there's some interesting things. Once you have a small amount of artificial gravity, now you can sleep in a bed. You don't have to get strapped to into a sleeping bag. You have the ability to have like a laptop sitting on a desk, or a mug with the coffee in it, some coffee in it sitting on a table. So those kind of creature comforts, if you will, things that are a little bit more familiar, start to come into play. Now, you're probably not going to drink in the same manner with 1/10 G, the fluid, the way fluids and surface tension work. You're probably going to have to adapt a little bit. But you can start to have plants that are growing in pots, or just the environment can be a lot more familiar. Now one of the things with Pioneer, though, we are also designing everything to be able to go into a micro G scenario. So if the ring despins, you're not going to have just things floating all over the place. So everything will be designed to be able to be secured for microgravity operation. But the hope is that the gravity ring portion of the station will have a certain amount of artificial gravity most of the time.
Right. Tim pointed out. one of the very important aspects of having even just a little bit of gravity is that you're accustomed to this on Earth, and in orbit, it takes a while to get accustomed to this. If you're in microgravity, if you've been, for some reason, you're tired of looking out the window at Earth and you want to read in a book or a Kindle or whatever, and you decide to take a break and you put that Kindle down, you know that when you come back, it's going to be there. In microgravity, you put it down and you go away and you come back, and now you have no idea where it is. It's floated off and it's probably stuck to a ventilation grate somewhere.
Yeah.
Yeah,
Although
I did notice in the renderings of Pioneer, all the interiors, there's I have all sorts of webbing on the walls, little crosshatch pattern. That's all Velcro. So you can stick stuff to the walls, right? Because you don't want your Kindle or your things floating away.
In case they shut off the gravity while you're out.
For the artificial gravity scenario, but
right
when it does go to micro-G, you don't want to have your pens just disappearing and floating off your desk.
You will definitely notice when they shut off the gravity. It's not like somebody flips a switch and it's off. Some fairly large rocket engines will light up to stop the rotation, and you will know immediately, oh, they're stopping the rotation.
Well, and there'll be
probably
a
red
warning, and it'll be scheduled.
Oh, right.
Say red flashing lights and everything. Yeah.
Yeah, it's not going to be like you're just sitting there drinking your coffee. Oh, there goes the gravity.
Right. Darn, it's out again.
Yeah, take it. So, what about the Voyager station? You mentioned, when you're working on Pioneer, you've got these considerations of, being able to flex between microgravity and that partial gravity, artificial gravity. Maybe even if not in one place, you've got the modules that are that kind of architecture. You mentioned modular architecture could be used in many different ways. When you're looking at the Voyager station design, are you also kind of thinking in that way of, how do we make this compatible with microgravity as well, or is that plan really to kind of stay in artificial gravity all the time? Yeah.
Well, most of the time, Voyager should be in artificial gravity mode. What the team's talked about right now is most likely de-spinning and going into microgravity once a year for maintenance. Maybe Tom, you want to talk about our lifeboats around the perimeter. There's a lot of questions about that and how we deal with that, because we have to service those to a certain degree in microgravity.
Well, for instance, when you want to attach those to the station, I would really be loath to tell a pilot, you have to bring in that craft and dock it to a station that's rotating, and you'll be under lunar gravity or Mars gravity or whatever, facing in the wrong direction when you're trying to dock. You definitely need to de-spin the station to get those docked to it. Now, undocking, that's easy. You just release and you naturally float away very quickly, accelerating at whatever rate the station is spinning at. But the docking procedure definitely needs a de-spin. And for various maintenance things, if you're doing some pretty heavy maintenance, like replacing an entire module solar panels and so on, you would want to de-spin for that.
Yeah, and right now we're in talks with Sierra Nevada Corporation to use their Dream Chasers for that application. We don't really know yet how long they can stay on orbit. It's not going to be a decade, right? Spacecraft degrade over time. So just with a natural cadence of maintenance, we're going to most likely have to cycle through those craft, and then they're really there as lifeboats. So medical emergency or some other emergency situation where people need to leave the station quickly, they can hop on those and land at any commercial airport. In any given 12-month period, however many of those have been detached from the station, we'd want to then replace those. But for the most part, the station is operating in artificial gravity. So that lets us do some more creative things, I guess. And because Voyager is so much bigger, we can start talking about food production and a lot of really closed loop on the water, for example, any of the waste products, having them be fully repurposed on station and not having to deorbit that mass.
Right.
One of the key parts of that is how much power do you have available? Often these reclamation and purification processes take a fair amount of power. And this is one thing that the Voyager station will have in abundance. The current design would be producing something on the order of 4 megawatts of power. And there's a lot you can do with 4 megawatts.
Yeah, that's unprecedented. Of course, you've got a lot of modules with a lot of people all ready to run their equipment, experiments and so on. But yeah, that winds up being a lot of power, so you can demonstrate things that haven't been done before on orbit.
Yeah, how did you guys end up with the Voyager design in the first place? I mean, I think that might be an interesting story. What got you to this size and scale of this kind of flagship project?
Well, there's a very simple equation that tells you what is the radius of the station, what they call the radius of gyration, how fast are you rotating, and how much centrifugal acceleration, how much artificial gravity do you get. That equation is the acceleration is equal to the spin rate squared times the radius from the center. So we had to look at, can you make it 2 meters in diameter and spin it at 60 RPM or 10 RPM or whatever and get plenty of gravity and people be happy as clams? Well, no, that doesn't work. There are limitations on how fast you can spin people and have them be comfortable, especially when they're turning their heads in different directions. And as it turns out, there's a lot of, I guess, research that indicates, well, maybe 1.5 RPM is about as fast as you can spin and still have it useful. People won't be, on Tim's side, people won't be throwing up.
Yeah.
So that put a limit on how fast we could spin it. And from there, if we want lunar gravity, that sets one of the other parameters, and that tells you here's how big the radius has to be to give you lunar gravity. In the initial version of this, we were looking at spinning at about 1.2 or 1.25 RPM, and that gave us a radius of 91 or 92 meters. We're thinking about going a little smaller, but still spinning at 1.5 RPM or less.
Yeah, one of the things about that is it's really unknown, right? The research that's been done primarily has been done on Earth with 1G environment kind of sitting on top of whatever rotation experiments being done. There's been a lot of studies through the years. Pretty much everybody has agreed that at least 1.5 RPM is safe. Some studies say you can go even faster, but it's a good starting point. And if we find that, especially on Pioneer, people are able to function just normally at 3 RPM, well then when we scale up to Voyager, maybe we've gone beyond lunar gravity to something a little higher.
Right.
So
or alternatively, make it a little smaller, which,
smaller.
I mean, there's advantages to having scale, right? Things are kind of cheaper in bulk, as it were. But on the other hand, you have to fill all those rooms. And so if you don't have to build it quite so big and have comfort, that could be an advantage.
And it offers such options as you may have the big ring like we show there on the Voyager rendering, and maybe that's at lunar gravity, but you could put some extensions and put a few modules out at almost double that distance, maybe a little more than double that distance, and those would be at Mars gravity.
Or fill in and have lower gravities. Like at the center of the station, it's basically a microgravity environment.
Right.
So you can scale anywhere in between and get different levels.
Yeah. And we don't know yet what kinds of, whether humans are going to need less than lunar gravity. I mean, we know that somewhere between 0 and 1 is probably optimal. Maybe it's at 1, but maybe it's half a G, maybe it's only 1/10 of a G. That would be fine to prevent a lot of the, the microgravity maladaptations that we've been seeing in the astronauts. So, and on the other hand, there's the opportunities for manufacturing and research, right? That might need some intermediate gravity level, and we're not really sure what's going to be needed yet.
There's a lot of research that can be done on Pioneer and Voyager stations. this is in an area that has cried out for research for decades now, and it's just that launch costs have been too expensive to be able to implement any kind of facility that lets us actually do the research. We don't know what are the effects anywhere between 0 and 1G. We've got lots of experience at 1G, trillions of human years at 1G. We've got probably millions of hours at 0G, millions of human hours at 0G, and we've got 3 days at 1/6 G on the moon. 3 days is not long-term effects. So essentially we have no data in between 0 and 1G. We desperately need those data before we start designing things that will take people out to the asteroid belt for 3 years.
Yeah, and ultimately, if we really want to have people living their lives in space, I think we're going to need 1G, or at least the ability for people to go to 1G on a regular basis, just, for muscle and bone density issues, to be able to come back to Earth. Otherwise, you're basically relegating them to, there's some sci-fi series out there, right, about people who can't then adapt to come back to Earth. So I think we're eventually going to scale up to that. It's just a question how long.
I'm going to bring up an image here because I wanted to get to this anyway. This is called Kalpana 1 or 2, designed by Al Globus, and was our first interview subject a few weeks back. This is actually not that much bigger than Voyager Station in diameter. I think it's got about 120 meter radius, something like that.
Can you kind of describe this to our podcast listeners? We're looking
I'm sorry. So yeah, we're looking at what kind of looks like the inside of a drum brake in a car. So it's a metal cylinder that is fairly flat. Maybe a tuna can might be a better description of it.
Yeah.
And it's got an outer radius of roughly 100 meters. You see some lights shining from the top, and I guess some communications towers and other things sticking out of one end. But basically, it's an enclosed, pressurized habitat where hundreds, if not thousands, of people might be able to live. And this would orbit, around the Earth fairly low altitude, similar to the International Space Station. It wouldn't be out, orbiting the moon or in the asteroid belt. So I see it as an evolution of where Voyager Station is going, and was just going to bring it up as a discussion of how can we get here? Like, what would be required to get to this point?
Yeah, I'm not sure if this is the end point. It's a innovative design.
Another stepping stone, at least.
Yeah, stepping stone. The next stepping stone.
Yeah, we've had lots of conversations about even the Voyager architecture, adapting that for much larger populations.
Right. So this isn't necessarily the only design that gets us there. Go ahead, Tom.
One of the things to consider is that with those dimensions, this vehicle, this station, would involve a whole lot more mass than a Voyager type of station. And even at tens of dollars per kilogram to orbit, the launch costs start to get significant, and even the environmental effects of launching that much material on Earth's atmosphere. And so you start thinking about using extraterrestrial materials for doing something like this, even in low Earth orbit. And one of the things that makes this possible is that Earth, as we all know, has an atmosphere. And if you're wanting to get rid of energy, which if you're bringing something from the moon or an asteroid, you'll be going very fast by the time you get close to Earth. You need to get rid of some energy. Well, you dip into Earth's atmosphere and let drag from the atmosphere slow you down and put you into orbit. And you can build the heat shields necessary to do that from the materials that you get at the extraterrestrial source. So you can you can actually build something like this more economically with materials from off Earth rather than having to send things up from Earth.
Nice. Yeah. So that then makes it tractable. I mean, we don't quite have the technology yet, but it seems like we can lay out a path from here to there with the launch costs, the increases in robotic capabilities, and just our experience doing things in deep space, at a commercial level.
Yeah, there is some research to be done there in terms of if you want to build a heat shield and all you have available is silicon, oxygen, potassium, and calcium, what kind of heat shield can you build?
I'm going to put on my chief operating officer hat here for a second.
Yeah,
I think one of the really exciting things that Orbital Assembly Corporation is doing is, like Tom was saying earlier, this modular approach, right? So building from Pioneer, which then feeds forward into Voyager, we could then, using these modular components, scale up to very large structures, and even like existing structures on an orbit. Let's say we have a Voyager Station Mark 1, we can augment that and add to it, and it can evolve over time. It doesn't have to be a one and done kind of, monolithic museum piece in 50 years. It can be a living, vibrant community.
It's evolving.
Yes.
Yeah, kind of like real cities are built. They're built kind of one block and one building at a time.
Yeah, the station becomes almost a mooring point to then build out from.
Right. Yeah, just from a technical point of view, if you're adding more and more mass to this big rotating structure, you got to make sure that your structural members can handle the increased loads.
Well, unfortunately, with artificial gravity that you bring about by rotation, one of the advantages is that if you're intelligent about how you design it, you can put everything in tension rather than having to have things in compression. This is one of the reasons that bridge abutments and pilings and so on are so massive. They're in compression. If you have a force pulling on something and something in tension, you can put a little thin wire there and it will handle the stress. If you start pushing on it, that wire can buckle. And so to handle it in compression, you need a much beefier piece of structure in between to handle those compressive forces. If you're in rotation, you can handle just about everything you want to do in tension, and that makes the structure very efficient.
And there's definitely limits to what you can do. We were talking about stopping the station for maintenance. There's certain things, structural members, even in tension, that you would want to upgrade if you were to do some big change to the architecture.
Right.
But I think the idea of modularity and doing things at scale is what's going to really accelerate people in large numbers going to space. If you think about even let's say your house, right? Your house is made up of very standardized parts, 2x4s, sheets of plywood that are 4 feet by 6 feet, standard doors that are 6 foot 8 inches high, right? There's all these standards and modular pieces that any contractor can go to any supply facility, and if they're swapping out a sink or a faucet or a hinge, everything is, there's a bunch of interoperable parts. Go backwards in time to log cabins where everything was very custom built. Every tree was unique, had to be shaped and planed and cut to size, and a lot of manual labor, right? To build a house was a very labor intensive, expensive process, where now you can build, a whole neighborhood very quickly. And in space, we've seen this more log cabin approach where everything is very custom, one-off, and that makes it very expensive, very slow. And so having standards, modular components, things that can swap in and out. My hope is in 100 years, Voyager Station Mark 1, there's still pieces that can be swapped out and upgraded, right? It's not like a throwaway piece of hardware.
Yeah, you build it right, it'll have considerable longevity. Well, we are getting toward the end of our hour, and I think there's quite a lot of questions that have come in. So how about if we take a few minutes to delve into some of those?
Sounds good.
Eric, you're on mute.
And I'm on mute. All right, here we go. I think we might have some time for a couple of these questions. We did get a lot, so I don't think we'll be able to hit them all. And Tom, this one might be a good one for you. Someone was wondering, how can you be sure that your stations won't suffer from the Janibikov effect, which is also called the tennis racket theorem or intermediate axis theorem?
Yeah, we talk about that all the time. Actually, I'm not being sarcastic there.
So if I understand correctly, this is when if you have something like a tennis racket or a hammer and you try to grab in your hand and flip it, it'll tend to begin rotating one direction. Then in the middle of rotation, it'll one of the axes will flip over really quickly, and then it'll continue rotating. And I believe I saw, and I maybe where it's the name, saw a video of something on the International Space Station just unscrewing a T handle from some module, and it just kept spinning in space. But every once in a while, the grip, would just flip its orientation back and forth. And
this boils down to some fundamental physics and something known as the moment of inertia. If you have a piece of something and three axes, there's an axis this way, an axis this way, and an axis this way. You look
so
at
kind of XYZ orthogonal axes. Yeah.
What's the moment of inertia rotating this way? What's the moment of inertia rotating this way? And what's the moment of inertia rotating this way? You want your rotation axis to have the largest moment of inertia by a factor of 1.3 or more over the others. As long as it's greater than that approximately 1.3, and I forget exactly the number there, it will be stable in rotation and you won't have to worry about that. Excuse me. But there are other rotational things that you need to consider, such as nutation. If you have something that's rotating stably and you fire a thruster and push it in one position to precess it a little, not only will you change the rotation axis, but it will nutation is difficult to describe, but it's a wobble of the station. Yeah. You'll excite this wobble mode, and you have to use your thruster firing such that you don't excite that nutation mode when you're precessing.
Yeah, and I think it goes without saying you need a balanced mass in a rotating structure. You want almost the same mass on either side, otherwise you get different kinds of wobbles.
Well, yes, and it will still be stable in rotation, but it will be wobbling in that stable rotation, and wobbling will be uncomfortable for people. And this is where Tim will say, no, we don't want to do that.
Yeah, no wobbles, please.
Well, it's yeah, I mean, it's basically like being on a ship at sea, right? You're gonna get nauseous.
Yes.
Yeah.
I guess if the wobble is consistent long enough, you'd eventually adapt. But
you get your sea legs.
Best to avoid space legs on and get your planet legs back when you land.
Right.
So we had another question on safety. When you're designing a station like the Pioneer Voyager, how can you build in safety to withstand for things like orbital debris or micrometeoroid impacts?
I'm surprised they didn't mention alien attacks. That's my biggest concern.
I don't know.
The Klingons coming.
Yeah.
Actually, I'll let Tom tackle this one at first. I've got some thoughts on it, but.
Micrometeorites being small and orbital debris having a limit on how fast it's going, we know how to design shields for that. There's a type of shield that's used on the ISS called a Whipple shield that's very effective at stopping small things. I think it'll stop a sphere of aluminum 1.25 centimeters in diameter without it penetrating into the interior. Things larger than that, they track with radar, and if you see something coming, say 10 or 20 orbits ahead of time, they know that it's going to intersect your position. You can fire thrusters and modify your position just a little bit so that it'll miss. Non-micrometeorites are probably the biggest problem. You can't predict them coming in, and radar won't see them in enough time for you to be able to do anything about that. But fortunately, the experience has been that the rate of significant size meteors hitting is extremely low. So it's kind of on the order of being hit by lightning on Earth.
Mm-hmm. Yeah, and I'll just add also that meteorites do make contact with Earth, right? I mean, right now, wherever anybody is watching, you are at risk of some interplanetary body smashing through your roof and pulverizing you. There's statistical risk related to anything we do, and so really our approach is, dealing with those high-level risks and the ones that we can plan for. Like Tom was saying, things that are just completely out of our control, or so statistically small that it doesn't make sense to have onerous measures to protect against it. That being said, our stations are designed with all sorts of redundancy and being able to section off portions of the station to where if there's a significant breach in one part of the station, the rest of the station isn't compromised. Emergency procedures, escape craft, that sort of thing, fire suppression systems, redundant software, and thruster controls. So there's, safety is always primary concern, especially when you have people involved. And planning for those likely accidents and those likely occurrences to the best of our ability is something that has been a conversation for some time. And we've actually got some really innovative ideas that are currently working their way through, patent process and such and design that we hope will significantly improve the safety on orbit. And also, I think something to remember, ISS has been operational for decades now. NASA did a very exhaustive survey of all the impacts and their effect on ISS. There's been a couple of things that have impacted radiators and solar panels. The number one effect that they've had, the most detrimental impact, are the small debris hitting like handholds on the exterior of the space station. Because when astronauts go to do EVA, their suits and their gloves catch on this rough metal from the impacts, and it actually causes tears in their suits. And so that's been kind of the biggest risk. They haven't, and it's been a while since I've read the report. I don't remember any MMOD actually puncturing the pressure vessel on ISS. Do you recall, Tom? I don't think there's been a.
I don't think there's been a documented case of a puncture due to micrometeor.
So, 20 years on orbit without any catastrophic impact isn't a very long time frame for one spacecraft, but I do think it helps to give perspective on the threat. Now, go ahead, Tom, then I got one other thought.
I might clarify something that Tim says. It's not that we are addressing likely accidents. We're addressing accidents that are more likely than being hit by lightning. So
yes.
They're relatively likely, but not likely.
Right. Yeah, it's not likely that the sun's going to come up. One other thought, and I think this is something that people really, why this topic comes up a lot, is there's an increasing amount of debris on orbit, right? And there's organizations that aren't being as responsible with their stewardship of the low Earth orbit, right? Really the orbital environment as they should be. There's a lot of companies working on that problem of debris removal and cleanup. That's not something we're focused on, but definitely companies that we are in conversations with, that's something they're working on. So it's we all have our role to play in this whole building up of people in space. We're not building launch vehicles. We're not building ECLS systems. We're not doing debris removal, but all the companies that are doing that are helping everybody. So
it's establishing a community.
Right.
Yeah, very much. Cool. Well, thank you guys. This was, I think, another fascinating conversation looking specifically at how the Orbital Assembly Corporation views the future in space. And I'm glad we were able to get into a few of the details and answer some of our fans' questions on the audience. But we need to wrap up now. So I just want to thank both of you for taking your time out of your precious day to come and speak with Eric and me, as well as to our guests. I mean, the people listening on YouTube and their engagement and questions. Thank you, Tim and Tom, for sharing your insight with us today.
You're welcome. It was a pleasure.
Yeah, absolutely. Really appreciate it. So anyone listening on YouTube, or if you're listening via podcast, feel free to reach out to us if you have any suggestions for future discussion topics, people you'd like us to interview. Just let us know. You can email us. Our email is ourfutureinspace@orbitalassembly.com. You can also find us on Twitter @ourfuturespace and Facebook @ourfutureinspace. So again, gentlemen, thank you so much for joining us, and thank you everyone for listening.
Glad to be here. Thanks.
Thank you.
Bye-bye.